When we want to find the slope of this function, what do we get? Well, we go through the same old, and we get minus f of x over h. Okay, so this is, well, x plus h to the third power minus x to the third power. And this is all over h. And what do we know? This must be as h approaches 0. So, whoops, there, better. Please be careful with the lengths of the stems on your h's and n's and a's and d's and so on, because, well, some teachers are a little picky. So, x to the third, 3x squared h plus 3xh squared plus h to the third minus x to the third, and this is all over h. So this is 3x squared plus 3xh plus h squared, because, well, the x to the thirds cancel out. And this is as h approaches 0. So, basically hand-waving the fact that h can't equal 0, thanks to it being in the denominator. What happens if h does equal 0, or is infinitesimal, so anything that's multiplied by h is negligible? Well, then, we end up with 3x squared. Well, what we get is, at P1, 1, we have y minus y1 equals m x minus x1. So, what is m? Well, hey, we said that m equals 3x squared. Notice that here we're getting rid of one step. As in, we don't just find m first and then plug it in. We just go straight in. So, 3x squared is 3 times x is 1 squared times, bigger brackets, kind of optional here. If you want to make sure that it's clear that this part is m, please do so, but otherwise, whatever. So x minus x1 is 1, and on this side, y minus y1, which is 1, equals 3x minus 3, y minus 1, so y equals 3x minus 2. Okay, now what do we do? Now we check whether or not this makes sense. We're trying to go through the point 1, 1. Okay, 3x minus 2, yep, sounds right, because, hey, it's upward sloping. As we know, x to the third is continuously increasing, except at x equals 0. And, well, we have to displace it downward a bit, because, guys, if we're going to go from the origin and then build up, this slope must not pass through the origin. It must pass below. Okay, now here, I really hope, guys, that we remember how to find slopes between 2 points. Between because that's what we do for a good number of questions in this section of calculus. So, -5, -1, and 2, 6. m equals y2 minus y1 over x2 minus x1. And this is equal to 6 minus negative 1 over 2 minus negative 5. So that is 7 over 7. So the slope here is 1. Now, often we have numbers that aren't quite so neat, such as here, where we have m equals y2 minus y1 over x2 minus x1. So this is 13 minus negative 6.6 over negative 4 minus 3. Yes, okay, I do realize we all, hopefully, remember this stuff, but, well, it is done in the texts for calculus, which I admit is a bit of a surprise. So, wait a second. There's a little bit of a problem here. All we're doing is, oh, we found the slopes between these pairs of points. What do we have to state? Well, depending on circumstances, we may have to state this. We may have to state that the average rate of change is the slope. So, 13 minus negative 6.6 gives us 19.6, and this is over negative 7, which is, well, how do we want to do this? We could say take 19.6 and times 5 and 98. Do you notice something there? 98 is divisible by 7. So divide by 7 and we get 14. So this is equal to negative 2.8 if we were to plug this into a calculator. Or, hey, wait a second, guys. 21 minus 1.4. What's 21? 3 times 7. 1.4 is 0.2 times 7. So, what should we write now? Just as we really should have written up here. The average rate of change here is 1. Yes, we probably already understand that it is a slope, but we need to demonstrate to our teachers that we understand it. So here, the average rate of change. You will notice a lot of various abbreviations as kids get, or students, not kids anymore really, students get more and more practice at this stuff, because the teacher needs to see less and less to know that you have a clue what you are doing. So the average rate of change is negative 2.8. And for this one, with the fractions, we would have m equals y2 minus y1 over x2 minus x1, which is equal to, well, y2 minus y1 would be this minus that. So 5 over 7 minus negative 3 over 8. And on the bottom we have x2, which is negative 5 over 3 minus 2 over 5. So this is equal to, well, 7 and 8 we can go for 56. So this would be 40 plus 21 over 56, and this is over 3 and 5. We can go for 15. So this would be negative 25 minus 6. Well, let's make some space, and we get 61 over 56 and over negative 31 over 15. So what happens, guys, dividing by a fraction is equal to multiplying by the reciprocal. So we end up with 61 times 15 over 56 times 31. 31 and 61 are prime numbers. So how can we do this? Well, all that says is that there's not going to be any canceling happening, which means that what we're going to end up with is 61 times 15, 915 over 56 times 31, 1736. So the average rate of change is 915 over 1736. All right. Now, let's say we have an example. That's, which interval gives the best estimate of the tangent at x equals 3 on a smooth curve? The tangent at x equals 3. Now, for most cases, you would answer C. So this would be the answer that most people would pick. But wait a second, guys. Let's say we have something that looks like this. And say, this is x equals 3, this here is x equals 2, and this here is x equals 4. And then x at 3.3 is somewhere around here. Yes, this is going to be an absolutely amazing estimate of what the slope is at x equals 3, right? Obviously not. Okay, so the answer that we should pick, though, because the question is just too vague. I mean, if it showed us a diagram of, this smooth curve, then sure, pick whichever one's appropriate. But even though, in general, the smaller the interval, the better, this is a bit vague for our purposes. So example 7. Identify whether each situation represents average rate of change or instantaneous rate of change. Explain your choice. Now, when the radius of a circular ripple is 4 centimeters, the circumference is increasing at 21.5 centimeters per second. So this is at a particular moment in time. So at an instant. Guess if it's average or instantaneous. Clearly, this is instantaneous. This is at one point, not between or over an interval. Now, Nico travels 600 kilometers in 6 hours. That's an interval of 6 hours. So this is an average rate of change. And let's say at 2 p.m. a train is traveling at 115 kilometers per hour. So at one particular point in time, it has a particular speed. Obviously, this is at an instant, so it's instantaneous. Yes. Okay. Now a stock price drops 19% in 1 week. 1 week is a time interval here, so this must be average. Now, water level in a lake rises 1.5 meters from the beginning of March to the end of May. This here is a time interval. Therefore, this must be an average rate of change. All right. In summary, average rate of change, well, here's where we started. Here's where we ended up. Find the slope between these 2 points. That's your average rate of change. As for whether you went straight line or whether you took some detours, it doesn't matter. Which is why average rate of change, well, velocity, average velocity is, hey, initial position, final position. This is very different from, say, average speed, which is initial distance covered, final distance covered. Say you're going around a racetrack. If you go 1 lap around the racetrack, where you began and where you ended up are exactly the same position. Your average velocity is 0. Whereas, hey, the average speed, no, that's not 0. Because obviously you went around the racetrack in that given amount of time. So, physics students are probably familiar with this, but some applications of average rates of change can be a bit awkward for those of us who might not have taken physics yet. Now, the instantaneous rate of change is the rate of change at a specific point. So, say we have a curve, and we draw a tangent line at a particular point. The slope of that tangent line is the slope of the curve at the point of tangency. So how can we find an estimate of this? Well, we can calculate the average rate of change over the smallest interval for which there is data. Now, the smallest interval possible is unreasonable. Why? Well, say we're trying to plot a curve for increase in carbon dioxide concentration in the atmosphere per year. Guys, every morning you have the highest concentration of carbon dioxide before sunrise. And then, after the sun comes up, photosynthesis happens, and the carbon dioxide concentration fluctuates through the day. Why fluctuates? Guys, morning rush hour is a thing. There are lots of cars spewing out carbon dioxide, and thus it depends on your location as well. Because, hey guys, boreal forest out in the middle of proverbial nowhere. Cars? What cars? So, This should be over the smallest interval for which there is data, because at smaller intervals, there may well be additional variation that your data doesn't display. That's if you're using an approximation, like, say, modeling real life stuff. On the other hand, if you're using a function, remember how mathematics is theory and reality, well, in theory they're the same. Reality would like a word. So, please be careful when you're dealing with application problems. Don't trip yourself up too much. Now, an estimate of instantaneous rate of change can also be determined by using the slope of a tangent drawn on a graph. Now, graphical solutions are generally less elegant than doing the math. But before we learn the specifics of derivatives and how to get derivations, it's all we have. Therefore, sometimes you might actually have to draw some graphs and some tangents and measure the slope of those tangents. But there is a problem. The accuracy of the data and of the sketch is sometimes, well, sketchy. So not very good, which means, well, you're going to end up with some numbers that are somewhat off. So because this is not as good mathematically, well, people came up with the rules that we follow when doing derivations, which we'll get to somewhat later. It is essentially the same sort of thing we did earlier, where we found, hey guys, the slope along this whole curve, no matter what x is, as long as h, the gap between your 2 points for your secant, approaches 0, we find a function for the slope. So instead of just, m at, say, x1, we found something a lot more useful, which was m of x. So we found m as a function of x. Now, various textbooks may differ. Some of them, for this section, they might just have you do concrete numbers, like plug in, x1 is equal to 3, and x1 plus h is 3.0001, or something like that. But the slope as a function of the x-coordinate is what calculus is really about at its most basic level, as in just derivations. Well, that's it for this section, and we'll see each other next section when we can get a bit further into the stuff of calculus.